Okay, in the spirit of moving on with this material, I will give a second opinion of Lecture 18. I think he does quite well with this lecture. I just want to bring out some of the more mathematical aspects and maybe give a different perspective on this. All right, so if we go, of course, we don't have to worry about this. All right, so slide 3. Here's a few things I want to say about this. So what this is showing is a discrete signal because it depends on n, and he's using the z transform. So this is a linear time-independent system represented by this transfer function, and the output is simply the magnitude of the transfer function times the cosine of the angle plus the phase. So there's a magnitude and a phase difference. Okay, so the key here is multiplicative. In fact, this is just a complex multiplication of this complex signal. So let me bring this out here in what I wanted to say, which is, just let me compare this to what we saw in continuous time systems. Okay, so in continuous time systems, we focused on the system's response to input signals with a fixed angular frequency, typically denoted by the symbol omega. Okay, now notice here there's this capital omega, which actually functions as an angular frequency, right? Because here we have this is a cosine. It's really a complex exponential, right? It's the real part of a complex exponential. You see the complex exponential down here. This is a real part of a complex exponential. The n functions as your time index. N equals 1, 2, 3, 4. It's like time 1, 2, 3, 4. So the omega is like your angular frequency. All right. So in continuous time, we do explicitly write the angular frequency as omega. Frequency appears as the coefficient of time in the exponent of a complex exponential. And you remember you had e to the j omega t. So that was commonly seen in continuous time signals. Here we have something similar. Here you have basically it's e to the j omega n. You take the real part of that, that's cosine of omega n. Okay. The response of an LTI system of a complex exponential is just equal to the frequency response multiplied by the complex exponential. Now the multiplication is hidden here. That's why I don't really like to do it this way. What he should do here, and let me go ahead and copy this so you can see it. Okay, so let me move it down here. I want to do it in this part here. So let me go here, and then we'll see if I'm set up correctly. Right. What this really is saying, it's really just a multiplication. We can write this entire sequence as the real part of a complex signal equation. Now, this is the real part of e to the j omega n. And this h of z is in fact complex, but h is actually can also be considered as a function of e to the j omega. And the thing about linear time-independent systems is that, or time-invariant systems, is that the effect of the system on the signal is just a multiplication. I should say more precisely, the effect of the system on a signal with constant frequency is just a multiplication. Right? It's a multiplication by the system response function evaluated at that frequency. So I can write the real part of this goes through here, and it gives me the real part of h of e to the j omega times e to the j omega n. Okay, so it's just a complex multiplication of the original signal. But the real part of this entire complex equation gives me what I observe in practice. All right, so that's how you can look at this very simply in terms of complex exponentials. All right, so that's what I said here. Yeah, the response of a linear time invariant system is just equal to the frequency response h of omega multiplied by the complex exponential. Here I'm talking about continuous time, so here I wrote h of omega. Down here with discrete time, we don't write it as h of big omega. We write it as h of e to the j omega. That's just convention. We'll get to that again in a minute. Okay. So to get the real response, we just take the real part of the complex equation. All right. So keep this in mind. It's helpful to compare your experience with continuous time and discrete time. And I'm going to give a summary at the end of this talk. So in discrete time systems, we focus on the system's response to complex geometric sequences, typically denoted by z to the n. All right, so that's your z transform, right? So the geometric factor z corresponds to e to the j omega in continuous time. Right. So in fact, that's what he writes here. He's writing e to the j, this big omega, because this is a little bit different from angular frequency. We'll get into that, but it plays the same role as angular frequency. All right. So we can write z as e to the j omega and basically get the same equation that we get with continuous time. Okay. So as I said here, the z representation is just a convention that's more convenient for discrete time. So we don't write it as a function of omega, we write it as functions of z. So the response of a linear time invariant system to a complex exponential is just equal to the frequency response multiplied by the complex exponential. I wrote h of e to the j omega. You can write h of z. It's the same thing. Okay. So these two things are very closely related. So hopefully you're seeing this theme coming through. All right, now slides 5 and 14, this is more cultural background. He talks about the effect of amplitude and phase on our perception of sounds. So you can see that the frequency point of view is very useful in understanding our experience. What he says is that when we listen to signals, it's more the amplitude of the different frequencies that we hear rather than the phases. And then he goes on to say that's not true if you have several frequencies that are close together, then the phases start to matter. But if you have whole tones, you basically just hear the frequencies and you don't really pick up the difference in phases. So this is, like I said, this is more cultural background. So if I flip through these slides, that's 5 through 14. I think we talked about this before, this kind of stuff before. So, yeah, okay, we'll pass through this. Okay. And you can listen to his lecture about this. He just says that that you don't, there's some differences you don't hear, there's some differences that you do hear. All right, now in most of this lecture, he's going to be talking about discrete time signals. So these are signals that have non-zero value at times 1, 2, 3, 4. So they appear as a series of spikes. So here he says discrete time frequency responses are periodic functions of omega with period 2 pi. So why is that? Well, the largest angular frequency that appears in the Fourier representation of a discrete time signal with sampling period 1 is 2 pi. This is because higher frequencies, when sampled with period 1, end up being identical to lower frequencies. And this is called aliasing. And you can look back at the previous lecture. He gives some examples of aliasing. For instance, right here, here's a low frequency signal. Here, as you can see, this is a discrete time signal. So the signal appears as spikes. This is cosine of 0.5 n. Now remember that typically of cosine of omega t, or capital omega n. So the period of this function occurs when 0.5 n equals 2 pi. Now 2 pi is roughly 6, so 0.5 n equals 2 pi means roughly 12. You can see that 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. So the period is roughly 12. You consider this as a low frequency because it takes 12 samples to get back to the same place. All right. Now this is very clear cosine wave because the sampling is low frequency. Now as you increase the sampling, this is cosine of n, so this means that the period is about 6. Okay. Then go down to cosine of 2n. This becomes a lot more choppy. It's more difficult to identify as a wave. Right? And then this one looks really strange, and then we get to here. We get to hear that in fact 2 different cosine waves will fit these samples. And then if you go even higher frequency, you can see that this very high frequency red has the same effect as this low frequency green. And we talked about how you can always replace this coefficient here by a number between 0 and pi. Right? So that means that we only need to consider low frequencies when we are looking at discrete signals. Now, we don't need to look at this high frequency, kind of fold it into the coefficient of the lower frequency. Okay, so let's go on here to the next place here. Right, so we have a highest frequency. So let me just say what he's leading up to. In fact, he's leading up to a derivation of the fast Fourier transform. Okay, so he's looking at discrete signals that repeat within a finite period. So in this case, the period is n. So we know that any discrete signal that is periodic with period n can be written as a linear combination of the related to the nth roots of unity. Right? So here he's showing the 8th roots of unity. And there are 8 different values of omega here that can produce a periodic signal that satisfies this periodicity. You could have omega equals 0. You could have omega equals 2 pi over 8. You could have omega equals 2 pi over 8 times 2, 2 pi over 8 times 3, etc. Okay. So we're actually going to be writing any periodic signal as a sum, as a linear combination of these roots of unity, as you see right here. This omega 0 is the basic nth root of unity, right? I mean, e to the j omega 0 is the basic nth root of unity. If you multiply that by any integer, you get all the other 8th roots of unity, right? So discrete time Fourier series, here you write these are the Fourier series coefficients, and then the original signal can be written in terms of these Fourier coefficients. So he calls this the analysis equation. You would analyze your signal into frequency components, and synthesis equation means you synthesize the frequency components together to get your original signal. All right? Now, actually, the relationship between a signal and its Fourier coefficients can be expressed as a matrix because it is a linear combination. So the question is that you can go back and forth between the Fourier coefficients and the signal using this matrix and the inverse of the matrix. But it's a lot of computation. The square matrix of side 4 has 16 entries, so that's a lot of multiplications. And if you have a larger signal, then you're going to have many more multiplications. So here's a derivation of the Fourier transform that I think may even be easier to understand than the one that I gave. Basically, this is the matrix multiplication you need to accomplish to get the Fourier coefficients for a signal x. Now, he wants to break up this matrix multiplication into pieces. And what he's going to do is he's going to look at the odd entries and the even entries and break those separately. Now, actually, you can break them separately, right? If I take these odd entries, 1, 3, 5, or 0, 2, 4, 6, the entries with even index, those are just going to multiply the coefficients 0, 2, 4, and 6. And these other entries are just going to multiply the other columns. So I could break this up into 2 matrix multiplications. The 0, 2, 4, and 6 multiplies an 8 by 4 matrix, and the 1, 3, 5, 7 multiplies a different 8 by 4 matrix consisting of the odd columns. That's not going to save any computation because you'd still have the same number of computations. However, the fact that these columns here have a pattern is very helpful. He goes into this in more detail in the lecture, but what these entries mean is that these are all 8th roots of unity, and you know there are 8 8th roots of unity, but we can index 0 through 7. The 0th 8th root of unity is just 1, and this one is going to be e to the j 2 pi over 8, etc. Okay, so these are all 8th roots of unity, and there's a relationship between these 8th roots of unity. Right? So he takes the even numbered entries and the odd number of entries, and he does some stuff with these, and he shows that you can get the Fourier transform based on these matrix multiplications, which are two 4x4 matrices, which is much smaller than one 8x8. Okay. Right. So he talks about that, and again, I encourage you to look at that. It is a very nice way of looking at it. I can say the difference between his and mine is that you have to work his backwards. Difference between his derivation and the one that I gave you in your worksheet, so you have to work his backwards while mine works forwards. He shows how an 8-point FFT can be obtained from two 4-point FFTs. But to apply his method, you first have to obtain the 4-point FFT. Then to do this, you'd have to find four 2-point FFTs. So you'd have to go from your original to four 2-point FFTs and build that up to 4-point FFT and build it up to an 8-point FFT. So I do it backwards. His trellis is backwards from mine. So if you see this trellis here, see I'm going for a 4-point, and then I get these, and then I get these, and then I go back again. He would go the other way. He would start with these and build up the 2 points, and then go back and get the 4-point. But it's still the same number of computations. It's still kind of a trellis structure. He only shows going from 8 to 4, but you would have to go from 4 to 2 and so on. Right? So let's see. In slide 32, if we go back to his slide here, he gives, it's this one here. Okay. He gives a systematic calculation of how many operations you save, and you can also listen to that in the lecture, how that works out. And it saves an enormous amount of computation when you have larger matrices. And he gives examples of that also. All right, so let me stop here, and I'll do a separate video on this second part of the lecture. Don't want to make these videos too long.